All right, so the first chemical reaction that we're going to talk about is a precipitation reaction. All right, and actually, it's actually what's called a double replacement reaction. Um, and we're going to do this in lab if we haven't already done so. If you're watching this after the lab, then you kind of know what it's about. Otherwise, we will do it in lab. And what it basically is you have two dissolved salts in what's called an aqueous solution. All right, aqueous, I believe last chapter we talked about a lot about aqueous. It just means a compound, a salt. Let's take like sodium chloride, which is a solid, and you throw it into water and it ionizes, it breaks apart into its ions. All right, so basically the way that you would represent this is you would just say NaCl aqueous. Okay, so they're showing you that in this beaker right here, you have sodium and iodide ions. You can't see it because it's all dissolved. And then you have lead and nitrate ions in this beaker, okay? And they are completely soluble. They are soluble, they are ionized, you can't see them. But when you pour them together, you get a reaction, okay? And the reaction forms a yellow solid or a yellow precipitate. And that yellow precipitate happens to be lead iodide. That's the solid you're forming. But your sodium and your nitrate ions that were back over here, your sodium and your nitrate ions, stay ionized inside of our solution. So you can see at the bottom I have the solid lead iodide, but I have dissolved in the solution is the sodium nitrate. Okay, so let me just show you the chemical reaction. You've got sodium iodide, which is aqueous, and then you add it to lead 2 nitrate, which is also aqueous. But when you mix the two together, you form lead iodide, which is a solid now, plus sodium nitrate, which is still aqueous. We're not going to worry about balancing the equation right now, okay? If you'd like to balance it, that's fine, but I don't want to put extra stuff into this because right now we're not talking about how to balance this. We're talking about how to understand what the chemical reaction is, what your products are, and how you know what the solid is. That's the big thing here. How did I know that the lead iodide is the solid? Because the book told me? All right, hopefully that's not your answer because that's not a good answer. All right. Yes, the book did tell me, but the book has rules that they're following, which you are going to learn as to how you know the lead iodide becomes the solid. Okay, and then how do you know the sodium nitrate stays aqueous? And how do you know how to write what the products are? Okay, because part of this is I might just give you this part of the equation, and you have to figure out everything else. Okay, so it goes to what's called a solubility list. I've kind of mentioned this in the last chapter, but now we're really going to talk about it. Now, this list is actually available to you on D2L. If you go there under, I think, I can't remember what the topic is like extra, it's not slides, it's handouts or something like that. All right, and it's under solubility chart. This is a chart that I will supply for you on the exam. All right, you just need to know how to read it so that you can understand how it works. Basically, what I suggest you do is to draw a line. If you don't have this printed out, I suggest you put this on pause right now. You go ahead, you print it out, and then you kind of take your notes on it. All right? Well, welcome back if you hit pause. If you didn't, go to pause now and do it, and I'll come back. Okay, so these top four, okay, notice has the word soluble in all of them. Okay, anything with a lithium, sodium, potassium, ammonium, these are group 1A metals. If you look at the group 1A on the periodic table, these are the metals that you see in there, plus ammonium ion. Any salt that has these in them is always aqueous or soluble. Anytime you see the word soluble, think aqueous. Okay, same thing for acetates and nitrates. Anything with these ions in it, it doesn't have to be lithium nitrate. I could have like lithium sulfate. If I have lithium sulfate, that is aqueous. Why is it aqueous? Because it's got a lithium. Okay, that's what the rule is. All right, we'll just keep going down. Chlorine, bromine, or iodine, halogens, they are all aqueous with the exception. Now we have exceptions. These now are solids. If I have silver, lead, silver or lead. We are not going to worry about the mercury compounds. Mercury is not very common. We are not going to be even using mercury or even talking about it. So pretty much if you have a silver ion or a lead ion, it's now going to be a solid. Otherwise, it's completely soluble. Notice what was one of our products. Yeah, like you can read that, right? Lead iodide was one of our products. Notice it's one of the exceptions in this rule. So that is how we knew that this yellow solid or precipitate is lead iodide. All right. And then finally sulfates, same thing. Sulfates are soluble unless you have, again, silver or lead. Get away with mercury. But this time also add calcium, strontium, and barium to the list. So these are solids. Otherwise, they're completely aqueous. Now down here, it's the exact opposite. These are always solids. So any metal attached to carbonate, iron carbonate, manganese carbonate, magnesium carbonate, copper carbonate, whatever carbonate, it's going to be a solid unless it's one of these, which is basically this rule right here. These are aqueous, 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 aqueous. These are completely all insoluble and they are solids. Okay? Anything with a carbonate, a phosphate, a sulfide, hydroxide, any metal, they are solids unless it's one of these four. And then in the hydroxide case, it's calcium, strontium, or barium. Okay? So that is how you read this chart. I'm going to actually erase everything on here. Oh. Hold on one second. Oh, that's not what I want. Let me. There we go. Erase all inside because we're going to be coming back to this slide periodically. Okay, so here's a simple thing. Silver nitrate, is that soluble or insoluble? Okay, well, let's look. It has a nitrate. Okay, so therefore it's soluble. So this is going to be aqueous. Calcium sulfate. Let's see. Sulfates are soluble unless it's one of these exceptions, and calcium sulfate is one of the exceptions. Therefore, this is going to be a solid. And finally, potassium carbonate. Notice potassium is one of the 1A metals. I can tell you right now, this is going to be aqueous. Doesn't even matter about the carbonate. Even though all carbonates are insoluble, unless it's a 1A carbonate, which is one of these. I believe it's a potassium. Okay? Pretty straightforward and pretty simple. All right, so the first type of reaction we're going to talk about, which was that example we saw previously, is a double displacement reaction. Okay? What a double displacement reaction is the cation of this molecule is going to pair up with the anion of this molecule. So my lead and my iodine are going to pair up to form lead iodide. So how do I get PbI2? Well, what's the charge on this lead? Remember, this comes back to knowing your formulas. Remember, we do the reverse crisscross? That was the trick. So this is composed of a lead 2+ charge and a nitrate with a -1. Make sure these charges make sense. Nitrate is -1, so lead is 2. All right, and then you break apart your sodium and your iodide. Sodium is a +1 and iodine is a -1. So my lead and my iodine come together, and since it's a 2-to-1 ratio, I need 2 iodines to balance out my lead. So that is how I get this formula, PbI2. All right, and then sodium nitrate, so my sodium here is going to pair up with the nitrate. Remember, you always write your cation first. So it's a 1-to-1 ratio, so you get sodium and you get nitrate. So that's what a double replacement is. Then I go back to the chart and I determine which one is a solid and which one is aqueous. All right, and if you look on the chart, we said that iodine are all aqueous unless it's attached to a lead, and anything with a nitrate or a sodium are always still aqueous. Okay, so that is basically how you do a double displacement reaction. Now, this down here is also another equation. This is what's called the complete ionic equation. Complete ionic. Okay, I'm showing what's still in the ionic form and what's not in the ionic form. So on the right side of the equation, this is still ionic because it's still aqueous. I'm kind of showing you what is inside of the beakers. And then this is PbI2. All right, it's not ionic anymore. Okay, so if we go back to this beaker, to this drawing, all right, what is it? So inside of these beakers, I have the the Na ions and the I minus ions. In here, I have the lead ions and the nitrate ions. That would be this part of the equation. I'm kind of showing you, this is what this beaker has, and this is what that beaker has. Now, after I do the reaction, what do I have in the beaker? Well, still floating around in solution in the ionic form is my sodium nitrate. But the solid now is my lead iodide. So that's what I'm showing in this equation. This is still, so now this is my beaker. This is still ionized, but this is now a solid. So this is what's called a complete ionic equation, and that's kind of what they're showing you. They don't show it to you in this particular equation, but that's the complete ionic equation. Then we have what's called a net ionic equation, and this is what is the overall reaction. Okay, first of all, the sodium and the nitrate, are they doing anything? Are they forming a precipitate? The answer is no. They are in the exact same state as what they started in. They're ionic here, and they're still ionic over here. They have not changed their states. They're still aqueous. Therefore, these are called spectator ions. They are watching the action, spectator ions. Okay, they are watching the lead and the iodine actually form a solid. Okay, so these kind of get canceled out of the equation, and what you have left over, Pb2 plus I minus, gives you PbI2, because you're changing states. These are aqueous, but notice this now is a solid. So this is our chemical reaction. That's our net reaction. That's why we have what's called a net reaction. Now, if you'd like to balance this, you can balance this at the end. So you need 2 iodines to react with every lead. Okay, this takes a lot of practice, guys. Don't expect, if you've never seen this before, don't expect to just automatically assume you're supposed to get this. There's a lot of stuff in here. We will definitely talk a lot about this in class and do a lot of practice problems. Okay, so this slide just talks more about what a complete ionic equation is and a net ionic equation. So in this case, they don't really show you, but your equation is Na2SO4 plus barium hydroxide, which is also aqueous, and this is aqueous. All right, and you do it, so this is what's in one beaker, the sodium sulfate. So this is the complete ionic. I'll put Ci for complete ionic. So my sodium sulfate breaks apart into 2 sodium ions and a sulfate ion. And the barium hydroxide breaks apart into a barium ion and 2 hydroxide ions. Okay, so now the double replacement reaction, the sodium is going to pair up with the hydroxide to form sodium hydroxide, which is aqueous. Okay, how do I know? Look on the chart. It is a hydroxide. Here's hydroxides. They're all insoluble unless it has one of these atoms on it, and it does. It has a sodium, so it's aqueous. Then the barium is going to pair up with the sulfate, and you get BaSO4. So let's go back to the solubility chart. Sulfates are soluble unless it's one of these, and barium sulfate is one of them, so that is going to be a solid or insoluble. So that's my solid. So now breaking this apart, sodium hydroxide breaks apart into ions. This will be a 2 in front of here, that's why there's 2's. But the barium sulfate stays as a solid. That does not break apart. So you have barium and sulfate ions give you barium sulfate. That now is the net ionic equation. What's my spectator ions? It should be the sodium and the hydroxide. Sodium hydroxide. They're aqueous on this side of the equation, and they're still aqueous on this side of the equation. All right. So this is kind of what you need to do. You need to write the balanced molecular equation. This equation up here is called the molecular equation. Okay, so there's 3 equations. There's a molecular equation, there's the complete ionic equation, and then there is the net ionic equation, and you have to be able to do both of them. In lab, we'll do tons of these. Okay. All right, so here's a problem. So let's do this. Lead acetate plus calcium chloride. These are both aqueous. I suggest you put this on pause and see how far you can get. All right, click pause if you haven't clicked pause. Okay, welcome back. So what I like to do is the complete ionic first. So lead 2 plus, I know it's a 2 because there's a 2 there, plus my acetate ion, which has a 1 minus charge, and then it breaks up to calcium has a 2 plus Cl minus. Now if you want to balance the equation and put a 2 here and put a 2 here, I am fine with that, but you do not have to. Don't worry about balancing. I want you to more understand what's going on here. Okay? So your lead now is going to pair up with your chlorine and get PbCl2. All right? And this is going to be a solid. How do I know? Go back to the solubility chart. Again, lead chloride is one of the exceptions. All right? Plus, you're now going to have, looks like calcium acetate. Calcium, see, I'm running out of room here, 3O2, and that's going to be 2 of them, and that is going to be aqueous, okay? Because all acetates are aqueous. So, the complete ionic is PbCl2 is a solid, plus Ca2 plus C2H3O2 minus. So my spectator ions are the acetate and the calcium and the acetate, because they're in the same state. So my overall reaction is lead plus chloride gives me lead chloride solid. Okay, so here you go. That's kind of confirming it. Plus, notice I have it balanced. Now, like I said, if you would like to balance it like how they do, I am totally fine with that. That is entirely up to you. If you are just like, well, there's 2 of them. I got to somehow account for 2 of them. Be my guest. Account for 2 of them. But these numbers don't mean anything when you're doing a precipitation reaction. All you care about is the overall reaction and what is going on. Okay? So here is a practice problem. It's very similar to, actually, is it the exact same problem? No, it's a little different. See if you can do this on your own. Okay? This is palladium in this case. Treat palladium as if it was like lead. So if you want to change that to lead, that's fine. So why don't you put it on pause, do the problem, and when we come back, we will redo it. All right, welcome back. If you haven't put on pause yet, put on pause and do it. All right, so let me do this. I'm gonna do palladium just because it's something new. So palladium plus NO3 plus sodium ions plus chloride ions. Like I said, treat the palladium as if it was like lead. It does a lot of the same things as lead. So I know this is aqueous because it has a nitrate. So my palladium is going to pair up with the chlorine to get palladium chloride. And if you treat this like lead, this is going to be a solid based off of our solubility chart. And NaNO3 is going to be aqueous. So in my product, I have palladium chloride, which is a solid, plus Na plus NO3 minus. Okay, these are my spectator ions, cancel them out. So whatever you have left over, lead plus, it's very similar to the past problems. Just so you know, this is not a typical thing. I just happen to have a lot of the same problems. So this is your net ionic equation. Okay, a lot to this. Practice, 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 and ask questions the next time we meet.